Right. Hey everyone. So this is the class for the signals and systems. Now we are going to study about the discrete LTI systems or LSI system, as we later explain. So okay, let me turn off my video. All right. So in the first half of the course, we have learn how to handle basically the continuous time system, uh, which consists of solving the integral convolution and then solving some let's say, basic differential equation. And then also we learn how to do like a Fourier series and then also a Fourier transform. So this also Laplace transform, obviously. So this is the continuity or the, let's say, the parallel of the continuous time analysis, which is the discrete time analysis. Here we have the um, discrete LTI system. So the way this course works is that first we focus on the continuous time system, and then after the midterm until the final exam, we focus on the discrete time system. So there are actually many parallels where in the continuous time system, we use what's called like a Fourier transform, a Fourier series, Laplace transform, whereas in the discrete time system, we just basically do the discrete version of those transforms. So I hope you understand what happens in the continuous time system so that it's easier for us to look at the discrete time system and yeah, be able to handle the discrete time system, how to analyze the system, how to perform the convolution operator, how to analyze the output of the system given a certain impulse response, and so on. So yeah, first is the signal representation in impulse form. So this is a discrete time signals, which is um, using the impulse operator delta. So now instead of having xt, now we have xn. So xn is discrete, whereas xt is continuous. So here the impulse is more or less the same, but of course n could be only integer. It's not possible to have, let's say, n equals 0.5 or n equals like minus 2.3 and so on. So the representation in the impulse form here, it says that yeah, of course, it's very important as a tool for signals analysis and the LTI system. And for the discrete time signals like this, we can actually get the impulse properties xn times delta n minus k equals to xk times delta n minus k. So both are um, discrete time signals, xn and xk. So suppose that you have n equals 0 and k equals 1. So basically this would be like a, or maybe this is only having a value if n is the same as k. So in that case, xn is the same as xk. And of course, it's different, both are 0. So if this is 3 and this is 3, well, this is always 3 and this is also 3. If this is 0 and minus 1, 0 here equals to minus 1 here because both of them are multiplied by 0. And we can expand this equation into xn equals to the sequence of the summation here. So xn is basically x0 delta n, which is this form, and this is x1 delta n minus 1 plus x2 delta n minus 2, and so on. So this way, we can get the value, for example, I want to know x3, then x3 is just basically x3 times delta 3, sorry, delta 0, which is 1 here, right? If I want to know x1, n equals 1, then this equals 1, and delta 0 here is 1, which means that we only have the value this um, of this term only. All right. Um, yeah, we can decompose the signal. This is basically the graphical representation of what we have studied just in the previous slide. So if I have a signal like this, x minus 4, x minus 3, x minus 2, x minus 1, and so on, we get x minus 2, x minus 2. What is x minus 2? X minus 2 is basically just x minus 2 times, yeah, times delta n plus 2. So that's if we want to find this. So this is just the identity. X minus 1 is x minus 1 times delta n plus 1. And x0 is x0 times delta n. X1 is x1 times delta n minus 1, and x2 is x2 times delta n minus 2. So xn in general is the summation of xk times delta n minus k. This is the same as in the previous slide. So this is basically the compact form of this. So we have xn, sum of xk, k is moving from minus infinity to infinity, and it's multiplied by delta n minus k, which is the same k as we have here for the same term multiplied. So yeah, that way we can represent the signal into unit impulse representation. So xn is xk times delta n minus k. Now the next step is to obtain the convolution response, and how to get the response is we first solve the differential equation, difference equation. So now we uh, refer to the equation not as differential equation, but as a difference equation. Difference equation, we do not have differential. Of course, we have difference now. Difference is, yeah, of course, it's a the difference between the two terms for, let's say, the current time and the time, the next step, the next time step. So difference equation here is solved, which is describing the system for a given input and initial condition. Or also we can make use of the linearity and the shift invariance. Now we have what is called the shift invariance, or it's basically the parallel of a time invariance. So if you have like a xt minus t 0, so this is called time. Yeah, shift is also time, but yeah, it's slightly different, right? Because it only takes integer value. So this is the shift, uh, or you can also say LTI. It's just the matter of the terminology. It does not really matter in the grand scheme of things. So it's called the convolution sum. The idea for discrete is we don't have differential, and of course we don't have integral. So if differential is basically difference, then integral is basically the summation. So this replace not integral anymore, but now we use sum, right? Just the integral. Okay. Now linear shift invariant systems, they have a superposition principle and also shift invariance. So superposition principle here means that yeah, it's the same as the linear part of the continuous LTI system. So if we have the input x1, we have the input x2, we have the input xk, yeah, of the time n, then it results in the y1 n, y2 n, and the yk n. Thus, if we have the input xn, which is the summation of am times xm of n. M is 1 to k, so which means that now we have a1 x1, a2 x2, and so on until ak xk of the nth time. Now we can represent this xn as all of this um, summation in the linear combination of the summation, which result in the yn, which is a1 y1 plus a2 y2 and so on. Yn here is the summation of am ym. Ym is the one that results from this this interaction between xk, yk, and so on. So this is the same m we have here and we have here. So basically, if we split the input into several different signals and then we process each of those split input, we will have the output, which is the combination of all of the inputs from different signals that we have. So that's the linear part, the superposition part, and then so this is the convolution summation. So if we have the input, this is the impulse. The output is called impulse response, which is Hn. Yeah, so this is impulse response. And then the shifted impulse input, delta n minus k, delta n minus k. Now we have the output h n minus k. And then if we have the input xn, xn here is the summation of the multiplication. So this is the one that we have before. Yeah, so xk times the unit impulse delta n minus k. Now we have the impulse response hn, and we have yn equals to the summation of xk times h n minus k. So this is from the principle of the convolution summation, and this is the convolution summation xn, the star of hn. So this is the summation convolution sum or convolution summation here, and then we have the commutative property, which is the same as what we have in the convolution integral. So you can switch xk times h n minus k, which is now equals to x n minus k times hk. So this is xn convolved by hn is the same as hn convolved by xn, right? So that's the the convolution sum here. Again, we have xk, we have h n minus k. Now h n minus k is the shifted impulse response. Yeah, so and if we have the input here, the output, this is the identity of the input. Now the output is we replace delta with h. So h again is the impulse response, and we obtain the yn, which is the xn convolved by hn, and then the commutative property here states that the hn star xn is the same as the hn star xn. So that's should be fine. Now there are several properties of the convolution. So again, the main idea of the convolution is how do we obtain the output given to interacting signals. In this case, it's X and delta, and we want to obtain the output Y. The interacting signals are X and H, and we want to obtain the output Y. And it's solved by convolution operation. In the discrete, we have convolution sum. In the continuous, we have convolution integral. So some properties of the convolution here, it's commutative and associative and distributive. So if we have two signals, yeah, this is the same as in the previous slide. And we have three signals here, xn, h1, and h2. We can either solve the first part, first block here, xn and h1 and first, or we can solve the second block first, h1 convolved by h2, and then we convolve the result by xn. The order does not matter, right? Because we have commutative also, and we have distributive. So xn convolved by h1 plus h2. We can sum this first, and we can get the the multiplication, not the multiplication, the convolution of each of xn convolved by h1 n plus xn convolved by h2n. And for causal system here, the definition is the response impulse. The impulse response is hn for a negative value of n, because it's not possible, right? That the response comes before the input, right? So that's not possible. So we have the causal system here, yn equals to summation of xk times h and minus k. Now we change the minus infinity to 0, so that it becomes k 0 to infinity. So yeah, we basically switch this x. So this is from commutation, right? So if we have xk h n minus k, we can switch this to x n minus k times hk. And then, yeah, since hk here, the value of k is not, not uh, it has no value for negative, so it's from 0 to infinity. Right? This should be infinity. Let me change this. Okay, now we are back. So yeah, it's infinity here. Now there is a difference between the finite impulse response and the infinite impulse response. So okay. Yeah, so for continuous systems, we will have what's called the IIR, or the infinite impulse response. So this means that it's a summation of some complex exponential which has no zero values for each finite interval. Whereas for discrete time, we have FIR or FIR. So impulse response here, it becomes 0 after some finite samples. Now, what that means is that in if you are familiar with like the solution of the differential equation, right? So suppose that we have solution y equals e to the minus t. Suppose that we have this solution. This is not going to be 0, right? There is no t that makes this thing 0. Of course, except at infinity, but infinity will not happen. So um, yeah, so we will not get the value of t that's exactly infinity. So this value of y is not going to be exactly 0, right? Whereas for discrete time, it is possible that we obtain some signal that goes to 0 completely after some finite samples. You will see later. Okay, so again, the difference is for discrete time we have fear of or the finite impulse. Whereas for continuous time systems, we have infinite impulse response or the IIR. Oops. Okay, so some examples here. So let's say we want to obtain the impulse response Hn. So this is again the impulse response, and we want to obtain the impulse response of the LSI system. Again, we do not have or we can call this LTI or LSI. It does not really matter again because we do not really call them time. Although some people call it time, but it's the same. Yeah. Here we call them shift. So instead of linear time invariant, we can also call them linear shift invariant system. So xn here, xn is the 5 times delta n minus 2. So this is the form of xn. And we have the output yn like this. Yeah. So we have the input and we have the output, right? Now, how do we get the input of the impulse response, which basically means that we have the input delta n being substituted into this equation. So now we have input 5 delta n minus 2. And now the output is like this 5 h n minus 2 delta. So this is the impulse response. Yeah, impulse response. And we can flip this or we can switch this. So we have h n minus 2 now equals to 1/5 of yn, and we have hn equals to 1/5 of n yn plus 2 because this is again the linear shift invariant system. Now we get that the output is like this. Yeah, so this is actually the other representation of the output. So if we have yn equals to 2 times minus a half to the power of n, we can write it as this, or we can also keep the same as this. The purpose here is that we can um, we have this relation between y and h, right? So h is y and minus n plus 2 equals something. Of course, we can uh, also have this. So 2 minus half n plus 2, right? Plus 8 times 1/4 the power of n plus 2, and this is all divided by 5, right? And it's the same as this, okay? And it's the same as this. N is more than 2, more equal than 2, which means we have put n minus 2 here. Yeah, sorry, I think, yeah, this should be n, yeah, n minus 2, that's correct. And then if we are interested to find the y plus 2, then this is going to be un, and this hn is the same as this, okay? So for discrete time and also for signal or system in general, we have the we could have a multiple representation that result at the same value. So especially for discrete time signals, these two, so these two, this and this, they are sorry, this and this, they are the same. So this could be the same as the one that I have written before. So yeah, we find the impulse response as this. We find the impulse response by basically plugging in the value of the input delta to the input here, and the output is the basically we change delta into hn, and we have the relation between hn and yn, and yn plus 2 is basically just yn shifted by 2, and we get hn is 1/5 times yn uh, times un. All right. All right, so now for the second example, we try to obtain yn, just the output of the linear shift invariant LSI system. If it's known that Hn is beta n times Un, and Xn is alpha to the power of n times Un. So yn here, of course, we use a convolution sum. As we see here, xk, we basically substitute this n with k, and h n minus k, we substitute beta to the power of n minus k times u of n minus k. And we use several properties of the unit step signals, where if k is less than 0, then uk is 0. So this is replaced by the lower bound or lower limit of 0. And since n minus k, we sum this from k minus infinity to infinity. But if k is more than n, which means that the value of un minus k is 0, so k here, the limit is n. So yn here is the sum of alpha to the power of k times beta to the power of n minus k, and it's beta to the power of n. So we kind of put this out, equals to sum of the 0 to n alpha beta minus 1, beta to the power of minus 1 k. So we have that. We have this part. So how do we substitute, right? How do we sum this? So if sorry, if you are familiar with the geometric series, what we do basically is if we have a to the power of k, where k is from n1 to n2. All right, so from geometry summation, we have sigma of a to the power of k from n1 to n2, and the way that we can sum those is by using this geometric summation. The denominator is 1 minus a, and the numerator is a to the power of n1 minus a to the power of n2 plus 1. Right, so now yn here, so beta n, we can pull this out. So this is 1 minus, since we have alpha beta to the power of minus 1, k here is from 0 to n. So n1 here is 0. So a to the power of a times, or a over b, to the power of 0, which is 1, minus alpha beta, alpha over beta to the power of n plus 1, minus 1 minus alpha over beta. So in other words, or in other representation, we can get by basically multiplying all of this with beta, we get this one. Right, so we have yn is the ratio between alpha to the power of n plus 1 minus beta to the power of n plus 1 over alpha minus beta. Now it is also possible to get a unit step response Sn of the system with the impulse response Hn. So Yn, the output here is the summation between x and minus k times hk. So k here is from minus infinity to infinity, but since we have the x and minus k, sorry, so this Sn is summation of k from 0 to n. So here k minus infinity to n of hk, right? And the impulse response here is hn equals to Sn minus Sn minus 1. So this is the unit step response, where this is basically u. So this is u and minus k given the unit step input. So impulse response, in other words, is a difference between Sn with Sn minus 1. So this is Sn. This is the input. If you have the input here, well, the difference is like this part, right? This part. All right. So that's the unit step response, but this is not very widely used for characteristics. For simulation, I think we could use unit step response, but for the characteristic of the system, we commonly use a unit impulse instead. How to obtain Hn from Sn? We get from this example below. So we obtain Hn from the linear shift invariant with step response Sn is 1/4 the power of n times Sn. So this is the step response of the system, which means that the um, output given unit step input. So this is Sn, and we can obtain the Hn, or the unit impulse from Sn minus Sn minus 1. So Sn is 1/4 to the power of n un, and Sn minus 1 is the 1/4 power of n minus 1 un minus 1. So we can factorize this into the summation, not factorize, but we can break this down into delta n plus 1/4 to the power of n u n minus 1. So this is 1/4 to the power of n un, right? So if this is this would be like a 1/4 0 plus u0 if this is n, if n is 0. So that means that we can break this down into delta 0 plus 1/4 to, let's say, 0 u n minus 1. So maybe the better way is we know that this is n, right? So this is like if n is 0, so we have this, this, this for this term only. Now this is the impulse. So this is the impulse plus the all of this. So it's shifted by 1. So the remaining part. So this one is this. Okay. Minus 1/4 to the power of n minus 1. times un minus 1. So we bring delta n here, or we bring this 1/4, rather we bring 1/4 to the power of n minus 1. It becomes 1/4 to the power of n minus 1 multiplied by 1 minus, so this is 1/4 times n, right? So it's uh, divided by yeah, 1/4, which then it becomes this delta n minus 1 minus 1/4 times 1/4 to the n minus 1 times u n minus 1. All right, so to do convolution, it's actually useful also to illustrate that with a table. So we can use a table to perform this convolution between hn and xn. Oh, sorry, this should be, I will change this. The arrow should be below the value where it's at time 0. Yeah, so now it's correct. So Hn is the sequence that starts at 1 uh, and also 1 and also 0 and also minus 1 and also 1. So 1 here, the second one is at time 0. So we can put this into this table. And Xn here, it starts at time minus 2, time minus 1, time 0, and times 2. So this is xn. So now what we do is we obtain the xn minus k hk. So it's useful to get xn minus k first. So xn minus 1, xn minus 1, xn plus 1. Which means that we shift this to the left, and also we could find xn minus 1. We shift this to the right, 0, 1 minus 1 minus 2, and xn minus 2, we shift this 2 steps to the right, 0, 1 minus 1 minus 2, and x minus 3, we shift this 3 steps to the right, so 0, 1 minus 1 and minus 2. And we get hk, right? So hk here, for example, if we want to find h minus 1, it's hn times x n plus 1. So that would be the hn, and that would be x n plus 1. So we have this x n plus 1. We multiply this with this. Okay. So this multiplied by this multiplied by this, this multiplied by this multiplied by this multiplied by this. We do not change the shift because we have done that already. So now it's 0, 1 minus 1 minus 2, 0, 0, 0, 0. This is same, right? 1, 1, 0 minus 1. So now this is 0 minus 1, 1 minus 2. And this is 0, 1 minus 1 minus 2. And yn here is the sum of all of them. So this is 0, this is 1, this is 0, this is minus 3. Sum all of this, minus 3, 2, 1. And this is minus 2. So we do not get the equation, right? So because this is the sequence, this is not the form of the equation. So this is the sequence, not equation. And the result is also in terms of sequence, right? So this is also not equation. Okay. Yeah, now we obtain the yn. Yn is 0, 1, 0, minus 3, 2, 1, minus 2. If we try to write that in a sequence form, that would be 0, 1, 0, minus 3, 2, 1, minus 2. Where we put an arrow here below the time, this time 0, right? So it's this time 0. All right. Yeah, so that's how we do that with the table. So next is we try to do that with some graphical interpretation, which is more or less the same as table. So basically, we shift some of the signals either to the left or to the right, and we multiply those shifted signals with some value from the impulse response, or you can also do the opposite. And also, we sum all of the shifted signals into um, this h times x. We sum all of this, and it becomes yn. So graphical interpretation of the convolutional sum. This would be helpful to solve the convolution if the convolved signals, if they are expressed in the graphical form. And the convolution sum operation, it involves some transformation of independent variables. And of course, the graphical interpretation of a convolution sum, it requires understanding the graphical meaning of the independent variable transformation. So these are some procedure. Now we try to obtain the graphical convolution procedure in using some of the methods that we have in the table. Now we can compute the convolution yn with the sketch of the xk and of the h n minus k. So for any fixed value n, we sketch xk and x n minus k. The signals are in forms of xn, right? So the xn, the convolution still is yn, is the convolution between the xn. I'm so sorry, convolved by hn, and we compute the multiplication of this as a function of k, and then we compute the summation as a function of k, and note that the summation depends on n and k. So I think it's actually easier to do that with the software, but yeah, let's try to do that here. So we have xn and we have hn like this. So xn, let's say it's a 0, 1, maybe like half, and then maybe like a 1/2, and then maybe 2. Hn is 1, 1, 1, for example, for 0, 1, 2. Yeah, so hk here, and this is the xk. Hk here, they are the no, the uh, impulse response, and this is the hk. We just change the domain, and yeah, it's shifted by -1. So that would be the so this is k, right? This is k. -1 minus k. So because this is all of these are the same value, it's actually reflected. So it's mirror, but we cannot really see because the values are the same. But this is flip mirror. So that would be n-1, which means that it begins. So the ending was from 0. Now it ends at -3. So okay, maybe I should put hk first. So hk here would be like this, right? So this is -2, -1, and 0. And that's -3. We pull this one to the left, and we pull this one more to the right, so it becomes a 0. We pull this one more to the right, it becomes 1, so on. And this is xk. So xk here is the same. So we kind of multiply this signal with this signal. So because there is nothing to multiply here, all of these are 0, because here we multiply only at 0. This is the one that has a value is at 0. And since we now multiply this from -1 to 1, the value that's possible here is also at 0, and so on. Yeah, we continue. And now we have all of these xk, h minus k plots. And we basically sum all of those. That becomes h and minus k of from 1, -1 to 6. We don't do -2 because the value is all 0. In fact, even the value at n-1 is also 0, but that's yeah, for the border, for the lower bound, and for 6 it's also 0, so it does not really matter. But yeah, we basically sum all of this from, from -1, or from 0 to 5. You can see the difference here, and you can see that 3 has the largest uh, from this. So yeah, maybe from this two, and from this also, it has a largest magnitude. Actually, it's easier to do this with some help of like application or visualization. Let me maybe we can do that in the class. Yeah, next meeting. All right. So now we continue to discuss on the some properties of the linear time invariant or linear shift invariant system. So I will just go through some of the other um, properties. I think the most important ones are the shift invariance and the linearity. We have done that already at the beginning. So memoryless and invertibility, this is more or less the same as the continuous counterpart. And the memoryless system here, the output at a certain time depends on the input at the same time. So yeah, it does not have any memory from the previous value, where k is the gain or the constant, and the impulse response of the memoryless system here is hn equals to k times delta n, right? And the invertible system here, so yeah, basically we just change this x into delta and so on. And invertible system, if the system is constructed in series with the original system, they will produce the same output as the input. So if we have hn and we have h1n, we convolve those two, it will be delta n. So hn here, note that it's an output of the delta n, and yeah, the hn and h1n, if they are constructed or they are set in series, then it becomes delta n, the original input. So the next the next properties is the causality. So causality condition here means that hn is 0 for negative n. So hn equals 0. So n negative, the output of the discrete LTI systems here, yn is the sum of the xn minus k times hk, or the yn here, we can of course flip this, hn minus k times hk, So that's yeah, the same. So if we have the causal input, we further have this n 0. So if the input is causal and the system is causal, so we can change this minus infinity to infinity, minus infinity to infinity, that becomes 0 to n. So this is h n minus k times x k. And that's, yeah, the definition of the output is. Okay. So this is an example actually from the previous one about the invertibility. So Hn here equals to Un, and for input Xn, the input Xn, we have the uh, output Yn equals to sum of this Xk, Un minus k, and that's basically just Xk. Just change this into n. Yeah. And the output difference here, it determines the input. Zn here equals to Xn, which is the difference between the output. Yeah, thus the system is invertible with the inverse system here, Yn equals to Xn minus 1. So this is this, right? So you have H, you have H1. H1 is the system, the inverse system. So if you have the output here is this. And if we have the system with the output here, output like this, they will become the input, right? Um, yeah, so z here equals x equals yn yn minus 1. The system here is invertible with such inverse system. All right. So the next example here, or the next property that I want to talk about, is the stability, which is the BIBO stable, or the bounded input, bounded output stable. And given bounded input magnitude, output magnitude is also bounded or finite. And if xn here if xn is less or equal than k1 for any n, then the system output here, yn, they are not more than some bound. So this is the yn. The bound here is k1, sum of the impulse response hk. And since yn is finite, all of this stuff is also finite, so it's less than infinity. And thus, for the system to be bistable, so there is no bistable system, it's just a system. For the bistable, the sum of the impulse response has to be finite, or it has to be less than infinity. Now, example 7, if we have a system with impulse response like this, so again, we can identify the stability from the uh, the impulse response. So if the impulse response is going to be finite, then the system is bistable. If it's not, then the system is not going to be bistable. So here, this is Hn equals to alpha 4 of n un. So the system here is bistable if yeah, the magnitude of alpha is less than 1, and the system is unstable if the magnitude of alpha is more than 1. All right, so let me change some the mistakes in this. Okay, then it's a constant coefficient difference equation. So this is similar to the constant coefficient differential equation that we have learned in the continuous time previously. So, but there are some differences. Actually, it's the method we use is a little bit different. So let's see. Right. So the response of the LTI or the LSI system, linear time invariant or linear shift invariant, they could be obtained by utilizing linearity and shift invariance properties. And the system response is obtained through convolution of the impulse response and the input signals. And the system characteristics could be determined by the impulse response of the system. And generally, the difference equation for linear shift invariance system, they are like yeah, sum of this ak times yn minus k equals to bk x and minus k. Yeah, this is the same as the differential equation, but again, instead of having differential, now we have difference or delay. So uh, we do not have like like d square of y dt square and so on. We do not have that, so it's uh, change or it's you know it's changed into like a y n minus k instead of the k differential, the k derivative. We have the n minus k um, difference equations for the difference because well it's the difference between n and k. So for x is the same. Or alternatively, we can shift this actually. So it's from minus k to plus k and minus k to plus k for the um, shift. So if you have like a y n minus one, that could be changed into like a y n, for example, if we shift everything by one and so on. And for causal system, we have m less or equal than n. And possible solution approach here is the iterative solution and the analytical solution. So iterative solution, it does not exist for continuous time system. So that's, I think, unique for the discrete time system. So the structure is like this. So we have yn. Yn here, they are the difference, right? So we have yeah, yn plus k. So actually, it's easier to look at the examples. So we will try to look at that, look at one of those examples later. So yn here, it becomes this, right? So the main equation here is this equals to like an, and then it's the yn minus k, right? So the right part is similar, but now we have the um, x, right? So we'll have yn, we'll have yn minus 1, we'll have yn minus 2. So here the difference equation structure is we have this yn, the difference of x and y. We could show it this way. Now, in this equation above, we know that xn minus k is supposed to be known. If also yn minus k is also known, then we can compute yn minus k. And we can compute that beginning from n equals 0. We need some initial conditions. Since initial conditions is usually assumed to be known, then it should not be a problem. And then the process has continued for the next n values. The value yn here could be obtained through iteration. All right, so this is, okay, sorry. This is the next example of the iterative approach. So we need to solve the difference equation below with the iterative approach. So yn minus half yn minus 1 plus 1/8 yn minus 2 equals to half to the power of n, where all of the conditions, initial conditions are 0. So the answer is that we can get yn here equals to this same, right? So we find y0, what is y0, we find what is y1, we find what is y2, and so on. So yeah, it's basically we solve based on what we know of the system, right? So if we don't know the initial conditions, we cannot solve that. Well, it's also the same for the analytical method, that for this uh, iterative approach, it's also yeah, important to know the initial condition. So y0 is a half of y of minus 1 minus 1/8, y of minus 2 plus 1. How do we know this, all of this? Well, it's from the fact that this is 0, so this n is 0, this is 0, and this is 0, and we have 1. Now y1 is half of y0, right? So it's no longer minus 1, but it's now 0. And it's no longer minus 2, but it's now minus 1. And it's no longer 1, it's now half. We have 1 half. And for y2, we have 7, 8. So that's the way that we obtain that. We do not, we may not get to the equation. So this is based on the sequence. So this is the sequence of the, difference equation. Um, it's not a form, not in form of equation, but it's in form of sequence. Okay. Now the next approach, this is more standard, is the analytical approach. So the analytical approach here means that we solve as we do usually with like the continuous time system, where we have the homogeneous solution and the particular solution. The homogeneous solution is we set the input to be 0, and we assume that the solution has an exponential form. The exponential one here is slightly different. So it's not a e to the alpha t, but it's a alpha to the power of n. And the equation here is called the characteristic equation, sigma ak times a alpha and minus k. So we basically sum all of this, which is equals to 0, and we get rid of a here. We also get this equals to 0. This alpha is called characteristic value. Oops. Yeah, so the rest of the explanation is the same as the continuous time system, except that, again, we do not use exponential in form of e to the uh, minus t or e to the minus 2t or so on, but we get the exponential in forms of a1 alpha 1 to the power of n, a2 alpha 2 to the power of n, and so on. So if the roots are all distinct, then the homogeneous solution is in this form. If some of the roots are repeated, then solution here is obtained by multiplying only once. Okay, let me change the. Okay, so by multiplying the corresponding characteristic solution by the appropriate power of n, for example, if a alpha 1 has a multiplicity of p1, while the other n minus p1 roots are distinct, we assume a homogeneous solution here in the form of yh, which is a1 times alpha 1 to the power of n plus a2 times n to the power of alpha 1 to the power of n. Sorry, a1 times n times alpha 1 to the n, and so on. So that's yeah, some of the homogeneous solutions. I think this one is not that much different from the continuous time system. And how about the particular solution, right? So of course, for analytical solution, we have the homogeneous solution and the non-homogeneous of the particular solution. Well, the particular solution here, we could find this YP from superposition principle. So YP is the sum of the BK times Y bar NK and minus K. And to obtain Y bar N, then it is assumed that Y bar N is a linear combination of Xn and X delay. So xn minus 1, xn minus 2, and so on. Right, so let's try this with an example. So, yeah, example 9. So I think this is the last example of this class, of this video. So we solve yn minus 3yn minus 1 minus 4yn minus 2, which is xn, where y minus 1 is 1, y minus 2 is 2, and this is the initial condition, and this is the input. So this is the initial condition. This is the input. And to obtain the homogeneous solution, we seek the roots of the characteristic equation 1 minus 3 alpha to the minus 1 and so on. So how do we obtain this? Of course, by setting this to 0. We basically change the yn minus 3yn minus 1 uh, minus 4y and minus 2. Yeah. So this is basically like a yn, so this is like 1 plus 3 alpha to the power of 1 minus 4 alpha to the minus 2. So this is from this. And alpha 1 is minus 1, alpha 2 is 4. Then YH here is A1 times the root minus 1 to the power of n, 4 to the power of n. And with assumption of the particular solution, yp equals to a3 times half to the power of n times un. The particular solution here is yp n minus 1, yp n minus 1, and equals to a3 times half to the power of n minus 1 times u n minus 1, which is we can get ypn, ypn minus 1, ypn minus 2, and so on. So yeah, we get the YH n, right? We get the YH n. Again, how do we get the YP particular solution? So to get the particular solution, we basically get this superposition principle. So we get basically this x. So this is from the x. It's in form of the exponential as well, and yeah, we get this x is a half to the power of n, so it's not that much different from x, except that we add like one constant here, a3, which means that we get a3 half to the power of n minus 1. Now, yeah, we substitute to the difference equation. So this particular solution, so first we know the homogeneous one, right? So this is the homogeneous one, and we know the particular one. This is the particular one, and yeah, we substitute to the difference equation, and for n not less than 2, we get the value of a3 times 1/4 and so on. So yp here is 1/21 times 1 times a half to the power of n un. The general solution. So this is yeah, this is from substituting the particular solution into the difference equation, and then we obtain the general solution here, a1 minus 1 to the power of n plus a2 times 4 to the power of n plus 1 over 21 times a half over n, the or that's multiplied by un. So if we consider the initial condition of the value where y minus 1 is 1, y minus 2 is 0, we substitute those and we get this equation. Yn equals to minus 1 third minus 1 to the power of n plus 16 over 3 4th power of n plus 1 over 21 half of the power of n un. All right, so that's the first part of the discrete LTI or LSI system. I think next class on Thursday we will try to continue this and maybe look at some of the Fourier series or Fourier transform for discrete system. Also, I think we can look further into some visualization, which I will try to show you in the next class. And yeah, I think that's it from me. Make sure that you work on the exercise in the classroom, my ITS classroom, to gain the attendance. And yeah, I will see you on the next class on Thursday, hopefully. Yeah, if there is no further announcement. All right. So yeah, thank you and see you next time. Bye.